Thank you. Go for it, Lika.
Okay. And so this is, I'm going to talk about Heliophysics System Observatory, but only in the context of heliophysics system science. And this is even more important in the era of exploration and big data. And as we know, human civilization has now essentially extended from the physical domain of the Earth to the neighboring domain of the heliosphere. And space-based commercial and government infrastructure has grown so much, and it's still growing so explosively in the past many decades that satellites are literally running into each other, figuratively and literally. Furthermore, humans have been living continuously in the heliosphere aboard the International Space Station for more than a decade now. And this human presence, as we know, will increase not only from NASA, but many other aspirational agencies throughout the world. And it is already happening in many other countries. So we are no longer really simply observing some domain beyond our reach. We now must gain that level of understanding required to develop and inhabit this new environment. To me, that sort of summarizes what heliophysics is. And, and I'll go through it some more, of course, but you heard Mark, right? Saying how we emerge from so many different stovepipe disciplines. Absolutely true. But that doesn't mean we cannot come together under one discipline, which we are making up, so we are in charge. So think of the domain of earth science. We often call it meteorology, right? Now, meteorology has no connection to the word earth science, but it encompasses every branch of earth science. So I'd say, think of heliophysics and adopt this term as embracing this connected system science. Oh, okay, interesting. So this is simply showing that, the concept of heliophysics sort of broadened with time. Our understanding began with a very local view. We started looking at the poles of our own planet through coordinated activity during International Polar Year 1, International Polar Year 2, and you can see it goes back to the 19th century. And then came International Geophysical Year, and then came International Heliophysical Year. And I think as technology developed and international coordination grew, we sort of began to view the Earth as more of a system. And this is where we are till we take ourselves out of here into the domain of the Milky Way. That might happen someday. Now, I'm going to give you a quick view of the different kind of science we do at NASA headquarters in the Science Mission Directorate. Our science is integrated. We have, of course, heliophysics, we have earth science, we have planetary science, we have astrophysics, and very recently we have included the biological sciences, which consists of really studying biology in microgravity and under intense radiation. So NASA science is interconnected, and heliophysics in that plays a very big role. And what you see here are some of the big questions that SMD has. Are we alone? You have heard this before. Going from origin of life to fundamental physics and chemistry, to cosmology, galaxy formation and evolution, to societal development and environmental impact, to environmental monitoring and space technologies, to planetary evolution, geophysics, and climate. I mean, you can find pretty much everything in the kitchen sink in the kind of science we do. So heliophysics basically make possible accurate predictions of solar phenomena throughout the solar system and its impact on Earth, planets, and interplanetary medium. In a nutshell, Earth science enable more accurate and useful environmental predictions, including weather, climate, natural and human-induced events. Planetary science, I cannot see what is, can this be? I cannot see my full screen. Is there a way to do that?
So I don't know why you can't see your full screen, Lika. We can see everything.
Oh, okay, all right, well.
Yeah.
It's also my aid if I can't see. So planetary science is, of course, very destination driven. We go visit planets, asteroids, trying to understand the basic formation of the solar system. And astrophysics has its quintessential question, really. Are we alone understanding the cosmos with the giant telescopes that we launch, really peering into as close to the beginning of time as possible? This is very dated. This chart is at least 10 years old, but I kind of want to show this to you, since I don't have a newer version of this, is that these are the missions from 4 of the science divisions. It doesn't have biology in it, that I talked about. So we have over 130 spacecraft today. And we have lots of small satellites, CubeSat, we have balloons, we have rockets. It's an incredible smorgasbord of data from all of this. And when we pursue heliophysics system science, we draw from these observations, no matter which division is sponsoring that. But not only that, we will often also draw from our ground-based observations and international observations and other space agency observations. So the goal is that, as Mark indicated, open science, we have to make our data open. And that's the only way we can access the data, but we have to make the data open and accessible so that we can actually utilize it. Understanding the universe, this is astrophysics, and I'm not going to belabor on this, but I'm leaving these charts with you. Anyone who is kind of interested in this particular area can go for it. As astrophysics is focusing on cosmology and Big Bang, and you can see the interconnectedness of these threads. What are the questions and how do we sort of pursue them? Now we pursue them with taking observations, of course, with telescopes, but we also pursue them with theory modeling, data analysis. That is very important. And of course, archiving our data. And I kind of want to point out, in each of these, you will see that heliophysics actually plays a role in each of these disciplines. This is, we're looking at Earth system science, understanding the Earth system science, it's understanding physical climate system, atmospheric physics dynamics, and tropospheric chemistry. And here, actually, of course, the sun plays kind of a fundamental role. but also our geospace environment in the world of ionosphere, thermosphere, mesosphere, troposphere, play a very important role in absorbing this radiation, but then relaying it back. Understanding our solar system. So this is, as I said, often is very destination driven. We're trying to understand each object in our solar system. And these are some of the goals of the planetary science observations of primitive bodies, which provides direct measurements of early solar system conditions. Planetary science observation of airless surfaces measures record of planetary impacts. We're trying to kind of understand the history and evolution of the solar system. Planetary system science and comparative planetology, where again heliophysics begins to play a big role. And this is ours, understanding the sun's system, which of course starts with the sun. We don't impact the sun, but sun pretty much impacts everything in the system. But sun is not the only player in this large heliophysics system. You can see galactic cosmic rays, for example, penetrating, coming from another galaxy entirely, and affecting a lot of space weather, technological impacts, and also creating chemistry in our lower atmosphere that very likely has a role in the climate modulation as we see it. And these are many of the topics, the chains that are drawn, you are going to be able to go into during this workshop. Probably not, but at least some of those. This kind of gives the complex system of coupled processes and phenomenon that we are. Something happens, it starts for us with the, I'm not going to go to fusion, which really generates the light source, but let's start with the dynamo, which provides, creates really regions on the sun with concentrated magnetic field that produces flares, coronal mass ejections, which, there is the whole phenomenon of coronal heating. We are trying to understand why is the corona so much hotter than the photosphere. There is a continuous blow of particles called solar wind. Sometimes it's just a breeze, which is that low level solar wind. And sometimes it can be gusty, like in a coronal mass ejection or some other transient events. And all of these sort of propagate the 93 million miles in the interplanetary medium, where flares generate energetic particles, ultraviolet X-rays, the magnetic fields evolve. We don't know if they change direction. Interplanetary shocks are generated, and then cosmic rays are coming from outside. All of these input then begins to interact with the outermost layers of Earth, starting with magnetosphere and then gradually penetrating into ionosphere, thermosphere, mesosphere, and lower down. Now, this particular chart kind of shows, how each one of these items, like energetic particles, what areas of region in the geospace does it impact? It impacts radiation belts, it impacts magnetospheric dynamics, it impacts ionosphere variability. The ultraviolet X-rays really affect density chemistry of upper atmosphere. So these are the chains. This is where the science lies. And we, with our heliophysics system observatory, try to get as much of these observations as we can. But it's a vast space, so it's a very difficult challenge. This gives, again, space weather's terrestrial influence. So you can see on the left hand, the very complex model of the geospace environment. It is very electromagnetically driven, but it is also driven by the radiative input in terms of, the XUV and ultraviolet energy from the sun. This is just on the right, you just see simulation, because we take our observations from different spacecraft and we try to create model and see with that model whether we can predict actually what is happening. It's verification and validation. And this is a model of Earth's magnetosphere, really, which is being impinged by solar wind pressure. So what is heliophysics? Heliophysics is an environmental science, a unique hybrid between meteorology and astrophysics, simply because we are dealing with components that are close to Earth. Our geospace environment has a lot more detailed information and can do validation, verification much more than our astrophysical sun. So it's a combination of meteorology and astrophysics. It has an applied branch called space weather and a pure branch, which is fundamental physical processes. And this has, started back in 1995, applications of directed science that was coordinated by National Science Foundation to begin with. And then came Living with a Star program, which sort of pushed space weather components, science with relevance from the NASA side. Then we did International Heliophysical Year, that was to galvanize the rest of the world. And we added the aspect of comparative heliophysics. So what we learn on our planet and what we learn about our science now can be exported to other planets and other sun. So heliophysics as a scientific discipline, it is one of the oldest and then one of the newest discipline. It started with its early successes in Explorer 1 in 1958 that discovered radiation belts, Mariner 3 in 1963 that detected solar wind, and now we are actually going there with Parker Solar Probe within 10 solar radii of the sun, touching the sun, taking in situ observations to get ground truth validation and verification of so many of our models. What is happening then, what we are finding is mind-boggling, and I'm not going to talk about that very much. It's absolutely brand new environment, brand new observations, brand new science. And then there is Skylab in 93, which played a phenomenal role, discovered previously undetected processes and conditions that directly modulate the Earth. That's kind of where the connection came together. These efforts set the stage for the discovery of the connected system of systems in the solar system that comprise the focus of heliophysics research. So this is past. And this system is driven by the interaction of three forces: pressure, gravity, and magnetism, for which we believe, and this is George Sisco, who was a pioneer in this field and led the Heliophysics Summer School in its early days. And according to him, for which the universal physical processes governing order and disorder have not yet been fully uncovered. So you young students still have some physics that you can work on. And then, of course, the results of this research are very important for, they have benefits with utility, both political and economic, to our nation and the rest of the world. So these are some of the examples of discipline-specific general laws or principles. So very quickly, I'll just go through this. Astronomy has Kepler's laws or HR diagram, expanding universe. These are things you're familiar with, right? They're so universal. Chemistry has periodic table, valence. Biology has evolution, double helix. Geology has deep time plate tectonics. Meteorology has Hadley cell, baroclinic instability. And so in heliophysics, the terminologies are solar stellar wind, magnetospheric convection, magnetic organization of matter, explosive energy conversion, and the rest. And you will go through that. And
Lika, you're at the first 20 minutes.
Oh, I have no idea where I am even.
Okay.
But well, I'll go as far as I can. So very quickly, this is the organization of the universe by long range forces. Again, these are charts that we began with during our first Heliophysics Summer School. And you can see very clearly, that heliophysics is driven by magnetic organization, whereas gravitational organization plays a very big part in astrophysics and planetary sciences. So I'm just kind of showing you this connection between remote sensing and in situ observations, connection between gravity and magnetic field. And we are very magnetic field oriented research entity, plasma physics. And this is yet another one, just stretching your mind if you want to exploit natural parallels between helio, astroplanetary, and Earth. There is comparative astrophysics and there is comparative planetology. I'm not going to say these are almost like fractal to me, because you can see these parallels of regions of space that we have given sort of identical name, heliosphere, magnetosphere. Heliosphere is actually sun's magnetosphere. Magnetopause, heliopause, it's the same thing. Heliopause is actually sun's magnetopause. So there are lots of interesting parallels here where we can take our knowledge and study them. Heliophysics coordinates with our exploration division or planetary astrophysics and biological sciences. I'm leaving this chart here just a little bit so you will be able to read what's there. Because I think I have a lot more charts and probably not as much time. And so remember, I already mentioned that Skylab played kind of a game-changing role in the early 70s, where we really kind of came to terms with the Sun-Earth connection. We established that the corona is hot and controlled by magnetic fields, that X-ray and EUV variability at Earth plays a major role in the ionosphere. And this is kind of the NOAA R scale. High-speed solar wind originates from coronal holes. And, this chapter might be rewritten after Parker and Solar Orbiter finishes their, observational phase and we understand more about them. But this comes from the knowledge in 1973. And so we recognize that solar particles impact Earth. Those have consequences. That's the NOAA S scale. And finally, mass from the corona is ejected into interplanetary space. So solar catastrophic events can impact Earth's magnetosphere. And this is a whopper. This is really big. This is what can take a power grid down and render us useless practically. And this is the NOAA G scale. Fortunately, it doesn't happen too often. Terrestrial space weather, you will see more about this, starts with basically, I'm giving you the time scale. With flares, we get a lot of ultraviolet and X-ray radiation, travels at the speed of light, 8 minutes. I showed the R scale. Then comes, sort of electrons and protons, which are charged particles. They have mass. They take 10 to 30 minutes to arrive. That's the S scale that can, affect astronaut health, aviation, satellites function, et cetera, et cetera. And then, of course, comes the coronal mass ejection. These magnetic blobs with matter, magnetic fields can take anywhere from 18 to hours to many days. It depends with what speed the CME is lofted and what is the condition of the interplanetary medium. And so this is just another way of kind of telling you that different components of the sun, light, which is radiation, magnetized beam, particle acceleration, have different kind of impact in our environment, interplanetary medium and our own planet. And these are their consequences from satellite drag, radio blackouts, aurora, which is the most beautiful manifestation, and of course, impacting health of astronaut and crew. Not going to go over this. All of you are very familiar that our society has become very vulnerable to the whims of the sun because of our technological dependence. And so these are our basic, I don't know that I need to play these movies, but while I'm talking, so these are our sort of basic questions, solve fundamental mysteries of heliophysics. So very science focused, understand the nature of our home in space and build the knowledge to forecast space weather throughout the heliosphere. This shows the complexity of the system we are dealing with so many different spatial and temporal scales. And you can see this, it can go from less than 1 second to 1 year in temporal scale to century level, right? And then you can go from 100 kilometer to 100 AU, 100 AU. And so to try to create models with the limited observations we have, it is really a huge challenge. Typically more than 20 orders of magnitude separate the largest and smallest scales of interest in any given problem. So it's a non-trivial situation. Now I'm going to move to what data we are collecting. We collect about 2 gigabytes of data every 15 seconds from I don't know, about 130 of our NASA spacecraft. And that's just from NASA. And this data is really our most precious possession, because it is with these observations that we unpeel the science, our question. We can have theory, but theory is not validated without observations. And that's why we create missions, to validate our understanding and choose between the multiple concepts that we generate. So here is our heliophysics mission fleet. There are 19 operating missions with 26 spacecraft, 13 missions currently in development, 1 mission under study. But you can see, we think, oh my God, 19 operating missions with 26 spacecraft, then we should be able to understand everything. But think of the volume of space, 93 million miles separate sun and earth. This is nothing. This is a drop in the ocean. But this is still something more than nothing. This is our, a visualization basically of all the missions, and I don't know how up to date this is. Here, magenta kind of reflects the missions in the region of thermosphere, ionosphere, mesosphere. Yellow represents solar observations and imagery of their remote sensing. Cyan represents geospace and magnetosphere. Violet represents heliospheric observations. And this visualization presents, of course, orbits of the recent heliophysics satellites covering the space near Earth, out to the Sun-Earth Lagrange point, L1, and finally, view of the current missions operating in the inner solar system. And of course, we pull, the NOAA satellites, the GHOST series, very much into it, as I mentioned earlier. And so the scale of data, there is currently over 8 8.7 petabytes of compressed data from one of the telescopes, AIA, on Solar Dynamics Observatory. Uncompressed, this would expand to over 20 petabytes. So, I mean, in comparison, the rest of the data looks minuscule, but trust me, they are all important, all very valuable, and this diversity of data allows us to pursue the science we pursue. And I show here the deepest ground-based telescope, which is taking extraordinary, exquisite data of small parts of the sun. And you can see that it's already outdoing SDO. So we have a lot to think about. We have a heliophysics digital library where the Heliophysics System Observatory comes together. It enables the scientific analysis goals of the Heliophysics System Observatory, basically. This is where provisioning and curation of scientific big data from many sources happen. You know, I think you were hearing earlier that it's important to have metadata, it's important to have standards, especially in the context of open science that we are engaging in today. Support for data analysis and modeling in multiple computational environments. And of course, the design and implementation of a collaborative open science infrastructure. You know, individual missions can do great sciences, but unlocking groundbreaking system science requires the HDRL. And this is work in progress. Let me quickly go into the application of course, you know, the tools of artificial intelligence, machine learning to utilize HSO data and accelerate science discovery. And, you know, space science is really has vast amount of data, and you know, deep learning is hungry for data. So what you see is that most learning algorithms kind of plateau as a function of amount of data. So if you give it more data, and that's kind of a deep learning took off, you know, it continues to outperform the traditional approach. This is such an amazing a movie that I really like to show it whenever I can. So if you start with just basics, artificial intelligence is just probabilities, but with vast computational resources because of the rise of the GPU. And it can really repeat onerous human tasks, things that used to take scientists months. But it also helps us make sense of complex patterns that are beyond the reach of our mammalian senses. And that's what you're seeing here. These are just dots, and we can infer patterns out of it. It's just amazing. I can see this forever. These are some examples of what we have done with such data. This is 40 years of solar data. The challenge was to create a homogeneous set of magnetograms, and we've taken ground-based historical data to high-resolution space-based data. And the question was, can we take low-resolution ground or space-based data from earlier decade and upscale them to the high-resolution data, say, from Solar Dynamics Observatory HMI? And, you know, all I'm saying is that the answer is yes. I'm not going to go into details of how this is done. If you want to see these results, please go to frontierdevelopmentlab.org and you will find technical report on each one of these. So here, what you're seeing is the input data was, this is the input data, SOHO MDI. Sorry, I think the numbering is wrong. So what we are naming is wrong. What we had done is we had taken ground-based data, GONG data, and we were able to upscale it to HMI. And this is actually upscaling MDI, which is a lower resolution version of HMI from SOHO. And we are in this chart, we are showing that we could upscale it to the high resolution HMI data. So there is a lot of information content on data if we can begin to utilize the right tools and do the right calibration. This is another really mind-boggling exercise that we carried out. And what you see here is that Solar Dynamics Observatory, in 2014, lost one of its sensor that was actually measuring the XUV, extreme ultraviolet data that is very critical for the ionosphere, because ionosphere absorbs that energy and gets energized. So the question was, okay, we have lost that. Now, can we really take all the other data, especially the imaging data that we have on SDO, and try to create a tool that can predict the loss of that sensor? And that's what you're saying. You have to go through process of training and validation, but now we can take the SDO imaging data and we can produce irradiance data that the MEGSE instrument on SDO was observing. How cool is that? These are like incredible things we can do with tools of AI/ML. And when you have created a synthetic data set like this, then you can have derivative outcomes. You can do auto calibration of filters, basically, that lose strength over time. So we have to underfly rocket, but you can do auto calibration on orbit. You can do thermospheric density predictions. And these are all pretty much state-of-the-art results. And how do you do better thermospheric density prediction? You are not using the traditional, say, proxy data like F10.7 or something, but you are actually utilizing the actual irradiance input. This is yet another one which is kind of really amazing, done last year. How can we observe the sun and solar irradiance from any perspective? We only have data from, solar EUV data from two different vantage points, basically from the two stereo spacecraft and Solar Dynamics Observatory, all in the ecliptic. But with that, we can create a tool that can give us solar irradiance measurement anywhere in the solar system. This gives you the detail of how this work was done. I'm going to just show you some results here. And this was done with a method called neural radiance fields. And so now, of course, we have developed, solar nerves, essentially, where there are mathematical tools for optimizing multiple viewpoints, which then renders novel views of that object. And that's what you're seeing. Input images are many different images of this drum set optimization tool, and then you have the full system in view. So this is what we got from just those two data sets, from stereo A and B when B was available, and Solar Dynamics Observatory. And you can see, you can infer values at the poles. You can infer values anywhere in the system you want. And from our previous attempt with SDO, we can directly then convert that into an irradiance measure. And you can do this for Venus, you can do this for Earth, you can do this for Mars. I mean, this has just been created. And so it'll be really fun to do some ground truth validation of these models with the data that we have or we will get. And this is kind of a view of the, this is a tool, this is a model. Now we have, as long as we have stereo and SDO data, we can create this. Well, the sun is waking up very clearly. I mean, you can see this in this picture, and this is quite a bit earlier. Today, we can clearly see that the solar cycle is outpacing what was predicted Right below on the lower left-hand corner, I have at least one movie that shows the innermost region of the corona that Parker Solar Probe has been investigating. It is mind-boggling what we see, the tangled nature of magnetic field and particles. This is also to remind us, and I know you will hear a talk about the Starlink satellite failure, and that happened in really ordinary kind of coronal mass ejection that we wouldn't have paid attention to. So our technology is becoming more sensitive, and therefore we have to pay attention to what's happening on the sun and get that knowledge shared with NOAA so that NOAA can then do the prediction.
Lika, you have 10 more minutes.
Okay, so this is the solar cycle. I'm just showing this, and all I want to draw your attention to is that the spectral solar irradiance that we don't talk about very much is very important, because while the total solar irradiance varies very little, the spectral solar irradiance can vary hugely. And that has a significant impact on climate in the way it modulates our ionosphere and tropospheric chemistry. So to highlight space weather occurs at all phases of the solar cycle. All I have done here is change the solar cycle from being horizontal to vertical so that you are not biased anymore. That solar minimum means nothing is happening. At each phase of the solar cycle, there is a lot going on. And we are approaching the solar max, where we are going to get big solar flares. We have had already minor radio blackouts. These are all possible. And I'm not saying we are going to get melted power grid, but this solar cycle is pretty active. But during the solar minimum, we get extreme galactic cosmic rays. That is very hazardous. We have a rapid accumulation of space junk because the UV radiation decreases in the ionosphere. So there's a lot going on. You can't take your eyes off the sun. Whatever you are interested in, concentrate on that, and you can study that, and you can make a difference. And this is just a sample showing that there is space weather happening every day, from solar minimum to solar maximum, captured through SDO, through total solar irradiance, and through the aurora. The aurora is happening all the time, right? Which means that there is solar storms that's creating storms in our geospace environment. This is again using our data, our observatory data. This is how we are learning, right? We actually saw the approach of a solar superstorm. It was a big coronal mass ejection that was not directed at Earth, and it missed us. Our spacecraft survived, but we got the data, and we are learning more about what energizes something like this. But we do not know what the consequences would have been had it actually hit Earth. This is kind of showing the CME structure. This is the modeling that goes on. I think I have another chart on that, so I will pass that. This is the same thing, kind of now going into the minimum phase of solar cycle, where galactic cosmic rays become very important. And just as I said, I kind of think of it as fractal, just as Earth is protected from solar energetic particles by magnetospheres. So, the sun has the heliosphere protecting the energetic particles coming from interstellar medium. This creates a space radiation environment of its own. There are different kinds of radiations generated from solar particle events, from trapped radiation inside the magnetosphere to galactic cosmic rays, which is the most lethal kind. I'm going to go fast because I just don't have time to go over all this. And this just kind of shows you, cosmic rays during solar minimum can be a huge threat. And because we had a very deep solar minimum in 2008-9, you can see that the cosmic ray increased at a record high during that time frame. These rays ultimately interact with our atmosphere, and we can feel its impact when we are flying on airplanes, especially over polar routes. This is like if you are a 1K frequent flyer, you can get up to 10 chest X-rays. What it does for us, we are still trying to understand. And if we are actually sending people in space or interplanetary space, that's just going to be even more. I'm going to go very quickly. This is sort of an integrated radiation protection strategy for Mars. So if we are seriously thinking about going to these planets, we have to consider what the sun is putting out, what the sun's magnetic field is, and how it kind of evolves the conditions around. This is essentially the birth, I believe, of interplanetary space weather when the two stereo spacecraft were in opposition in the orbit around the sun with SDO and SOHO in the middle, when we could see the entire sun. That was an amazing moment. So there was nothing, no significant eruption that could detect, that could escape our detection. I would still say that the next frontier in space weather forecasting involves the uninterrupted tracking of storm clouds from the sun to the planets. And these are the 5 telescopes on stereo, kind of giving us that the first sample of what is possible when solar wind was no longer just solar wind, but we could actually see it in this storm. The new Punch mission is going to concentrate on a part of this, which is the lower part of it, really sampling that environment and giving us better understanding and better prediction. These are just kind of showing how our in situ detectors on stereo, our in situ measurements of solar wind plasma and particles at L1, all together, how we are really understanding the science that we are after. These are images. We live with this star. The entire solar system lives with this star. These are the models that are being developed at Community Coordinated Modeling Center with all of these observations. And these are getting, it started a long time ago, some 15 years ago, and they are truly sophisticated today, where we can do some really good prediction, even on other planets. And so these are the reasons for developing this predictive capability. Of course, human safety. As we know that human astronauts will travel to the moon, Mars, and beyond, where natural shielding is considerably less. So we have to know the radiation environment. Spacecraft operation, because energetic particles accelerated by solar storms can cause onboard computers to reboot, introduce confusing noise in cameras and other digital sensors. So we have to do this kind of prediction. And then, of course, the most important part for us is the scientific research. Sorry. I mean, the observations we gather, sometimes they're serendipitous. It's mind-boggling. With stereo, we captured the images of a cometary tail disconnected, and we actually have a much better understanding of this. It's a magnetic disconnection. It's not just radiative energy. I'm not going to go through this. This is all on comparative planetology, space weather on Mercury, because we have data from Mercury. We have Messenger, we'll have Baby Colombo soon. Space weather on Mars, we already know so much more than we knew about 10 years ago.
Lika, if you could, time's about up.
Okay.
If you could just.
This is almost, I think I'm towards the very end. This is again
Great.
kind of showing ground truth verification of radiation on the surface of Mars with MSL red. This is kind of where we are, Sun, Earth system science. We came, the growth from a consuming science to a producing science. What does it mean? It means that we took resources from the world to do our curiosity-driven science. But now what we are doing is actually of relevance to life and society. And heliophysics, I say, is a new discipline. There are textbooks of different sorts. There are you young people, students. We have so now trained over 500 of you. There is Jack Eddy postdoctoral fellowship. The next generation trained heliophysicists. I'd like to see us embrace the word and define it as well as we can. Star-planet connections, these are the consequence of connections between stellar and planetary dynamos on environmental conditions at planetary surfaces. These are, I'm showing this, and I think I have one more chart that gives you sort of areas of research that is still being explored. And finally, I'll just end with this, and you can read this. Heliophysics from a whole solar system perspective. We need our heliophysics systems observatory, but that is wholly inadequate. We have to get every observation that benefits us from wherever they come from. Thank you so much.
Thanks, Lika. Nick, do you want us to take a few questions right now, or wait until
Absolutely.
office hours?
Certainly, if people have general questions now, that would be great, and also specific questions. I don't think we talked to Lika about hanging out for office hours, but Lika, if you can, over the next half an hour or so, if you can stay on with us, and people have specific things that they want to talk to you about, that would be great. Does that work?
Yes, I can do that.
Great, thank you. So, but any specific questions now that anybody wants to raise? It was a broad, there was a broad sweep of all of NASA's science in one fell swoop. So there's either lots of questions or it was overwhelming.
And Nick, I would recommend that people raise their hand and ask the question rather than doing it in chat.
Okay.
Good, Sky.
Okay. Hi, good morning. So right, we have all these science divisions, but a lot of what I sort of heard was trying to get some crosstalk to happen. Especially I was, looking at the models and I got a little bit sidetracked because you said I work on MAVEN. So it's like irradiance, energy input to Mars and Venus and Earth, and applying all of these similar processes and methods there. So how can we come together and work on that? What's the best way to start that crosstalk?
I would say start small, bring it up here. It would be a great idea if we actually solicited, from all of you ideas that you are working on or would like to work on, right? Because we need to see the level of interest in the community where there is work going on and how do we feed into it. Because remember, these things are evolving in parallel. I mean, it's like we are learning from a fire hose, and I kid you not. You think you are doing this? I'm doing this. And I've been at NASA for 30 years. It just doesn't slow down.
Right.
So, but that's what's kind of awesome about it too, right? So I think for the purposes here, it would be great to get your comments, input, ideas collected, which could be shared, then, people like me can take it back to headquarters, to the respective stovepipe disciplines that we have, and engage them in such discussion.
Yeah, absolutely. Then sure, one thing that I did, I just got back from CEDAR a couple of weeks ago. And, I think that if we see one phenomena happening at Earth, then the same thing's happening at Mars, and they must have a similar starting point, I guess. And that's maybe one way to start the conversation.
Yeah, there are many ways thematically we can create these comparative heliophysics questions. And I don't know, I guess this is virtual because I know Nick does actually a really good lab, kind of trying to bring that home.
Right. Yeah. Thank you so much. This was a great talk.
Thank you.
Mohammed, you have a question?
Yes, thanks very much for the interesting talk. So I had a question about the influence of gravity on the CME propagation. So from my knowledge, I think in like usually in the simulations of heliospheric CME propagation, the influence of gravity is usually neglected. So although their masses can be very close to the mass of a small asteroid. So I don't know why the gravitational influence is neglected in these simulations.
Simply because it's another complexity. Think of what we are already dealing with. So people start looking at order of magnitude, you leave behind second, third order terms, not because they are not important, but it becomes overwhelming. It's just the simplest, it's a funny description, but, whenever you're starting with a large object, what do we say? Let's start with a spherically symmetric geometry, right? And then we add complexities to it. If we understand the system really well to the point where the perturbations made by gravity would become significant for us to realize, then I would say it's at that point that it will be added, perhaps. I'm just speculating because I do not do this complex modeling, but that would be my guess. But there are other modelers here in the room who can take a shot.
Okay, thanks very much.
Anyone else? Nick, we're at the top of the hour, so I don't know whether you want to just roll into office hours, give people a break.
So
I think we're technically scheduled for a break, right?
We are technically scheduled for a break. So if you need that, fine, Lika, I don't, do you need a few minutes to either get some lunch or sort yourself out? Or would you
Are
rather?
you asking me?
Yes.
Oh, well, I'm going to continue to prepare to leave for the airport.
Okay. So if can you hang on for half an hour? Okay. So if people have questions for Lika, maybe now's the time to get them. Otherwise, we will take a break, and you can either take it whatever bio break or lunch break that you need, or meal break, and we'll be back with our regularly scheduled program at the top of the next hour. So 1 p.m. East Coast time, which is 11 Mountain time, and I'm not sure what time it is in India. So great. Ivan's got, we've got a bunch of questions for you, Lika. It's still going. So can you see the hands raised, Lika?
I'm seeing the hands raised, yes.
So You can just call on people as you see fit.
Oh, okay, okay, I can do that. Ivan?
I frankly had a quick logistics question about office hours in the schedule.
Yeah.
Nick.
Yeah.
So what are they supposed for?
So this is to, since we were in the virtual case, so if we were in person, you'd have an opportunity to like collar the speaker at the podium after their talk was done and ask them some questions, or get them in coffee, or have lunch, at the lunch break, right? And sit down and talk to them. So this is our sort of version of that. So if you've got questions for us, certainly you can ask us. If you've got questions for the speakers, you can ask them. And so that's the role of this, is to provide an opportunity to interact with the speakers once they have finished their talks.
Oh, great, thanks.
Thank you for asking that, because I know we've been doing this for a little while and I forget to explain that. So great.
Next is
Yeah.
Murthy.
I think Yoshita was before me.
Oh, okay. I just see them linearly.
No, that's okay. Murthy can go ahead.
Yeah, my question was for Lika, and I wanted to know, so I think it would be really great to collaborate more. This interdisciplinary collaboration sounds really awesome. I think one of the problems I've had, and I think others have also had, when you're working with spacecraft data and you'd like to incorporate data from other spacecraft, it's not really easily accessible. And even when it is accessible, the data is not really in a level 2 data product format. And so I'm just kind of wondering if there's a plan to sort of centralize the data in a way that makes more sense than the PDS, which seems a little not super centralized. That would lead to cooperation.
So you know that PDS belongs to planetary data science, right? I am in heliophysics, but that doesn't mean we can't have conversation. And why are we doing this summer school? It is to have this conversation and to serve better in future, to create what we speak about, not just talk about it, but make that. And, in the spirit of sort of open science, HDRL, we are doing a lot, but this is all happening all at once. So we are all kind of overwhelmed all the time. So I would suggest, as a product of this virtual workshop, if you guys can come together and form maybe 10 areas that people think would be really awesome to work in, and write down the kind of data you need. Because when we start talking about data and every division's archival process, we get lost very quickly. But let's focus on the science you want to do, okay? And say these are the things we need. And I think we can handle that better. I'm just throwing ideas. Please give your ideas. This is in the spirit of open science, open discussion.
This is Nick, and I'll just say that so we'll be using some data from a few different ways of accessing different types of data, including CDAW, and we'll have some examples from that for the heliophysics and space physics data. So that'll be happening in the next couple of days.
Awesome. And for future, I'll tell you, we are going to be hosting the 4th Eddy Symposium in person, which brings students, the Jack Eddy Fellows. And this is this kind of theme of open science, open data, cross-cutting fabric is sort of the thematic background for that. And we are working to figure out how to make this happen. So we are also thinking.
Great, thank you so much.
And Anvisha? Anvisha, how do you pronounce your name?
Anvesha.
Anvisha, okay.
Hi, really nice talk, thank you. But my question is a bit sidelining from the heliophysics into sustainability, because you said we are collecting a lot of data, like there's some GB per 15 seconds. And I was just wondering, in terms of saving this data and processing, are we also taking care or thinking about the carbon emissions associated with that? Like, what about the sustainability and heliophysics aspects?
No, I don't think so. But, no, we're not thinking about it at the heliophysics level. This is an overarching issue. So this happens perhaps at SMD level, but even higher up, inside NASA level.
Oh.
Because this is not just a heliophysics data problem, right? So we all can't do everything.
Okay.
So sustainability is absolutely very important, and you do it wherever it makes sense. What my fear is that we sort of get trapped by sometimes these buzzwords and drive ourselves bananas to fulfill those obligations. And that can be detrimental as well. So at an overarching level, there are people thinking about that, yes.
Okay, great, thanks.
I don't see any more hands.
There's one more.
Oh, yes.
So Yoshida.
Yoshida, yes.
Yes. Hi, Lika. That was a brilliant talk. So I was thinking, I am right now trying to study the evolution of CMEs through the heliosphere, and I'm looking into the in situ observations of the solar wind near Earth. So what I see is, even though we have good data, in situ data of solar wind, even then we do need multiple fleet of spacecrafts to be able to, kind of formulate a 3D perspective of the CME, which is incoming probably, or any interplanetary structure for that matter. But do you think at some point of time we'll have to make a trade-off between the number of spacecrafts that we're sending up and the data that we're having, and intelligent techniques that can help us, make it maybe probably predict or formulate a 3D
Or
picture
make
of
this whole
something?
thing sustainable in the previous words, right? Because we can't do
Maybe,
everything.
yeah. So is it yeah, exactly.
So I'll tell you, I have created big missions, and I have sort of removed myself from that world a little bit. And I am almost 100% committing myself to the utilization of our observation. Yes, I said how much data we are getting. What I didn't write is how much of that data are we using every 15 seconds. Because human beings simply cannot do that. That was my point about AI/ML. We absolutely have to bring the tools that can help us. And so in heliophysics, I am very much engaged in that, very much. So where the future will be, I don't know. We will still do missions. We will still need observation. There are certain kinds of observations you must have. But we can also learn a lot more than we have learned if we can really utilize all the data we have collected over decades.
Great. Thank you, Lika. I'm not sure if there are any other questions that people want to follow up on.
I'm going to leave this open.
Okay.
And if I hear voices, I'll come back.
Okay. If you hear voices, check your meds.
Yeah, I'll do that too. Thank you very much for all of you who are participating from all different time zones. You know, this is how we grow the community.
All right. Thank you, Lika, for a fine talk. If you're still on, please show your appreciation with either emojis or something, and to Lika's talk, and we will and have a good trip, Lika.
Thank you.
Okay. I'm going to be off I'm going to go off now, and we'll be back near the top of the hour. Please be back a few minutes beforehand, and we'll start the afternoon activity, or evening activity, or morning activity. The activity for the day. All right, so I'll see you in a little while. Shelly, if they're there, do you want to either pause or stop the recording?
I can do that. We will have all of the recordings posted at the end of the week afterwards. I do have Lika's slides. She just sent them to me. So I can drop those in Slack if everybody would like to have them there. And then we will also get those posted onto the Heliophysics Summer School webpage as well.
Yeah, so I think it would be great to have them in Slack just for our temporary use now, but then of course there'll be a more permanent home later. Yeah, keep in mind that the Heliophysics Summer School page has under the resources section has all of the previous lectures and slides, lecture recordings and slides from past years all the way back to the beginning of time, as we like to count it.
And Nick, just a quick reminder, I know not everybody's come back yet, so but we had a couple people that didn't log in this morning until 9, so I think there was some confusion on the start time. Just to remind everybody that it is 8 a.m. Mountain Standard Time, or Mountain Daylight, whatever we're on these days. Mountain Time.
Yes, great. Thank you. Okay. We will give it a couple of more minutes for people to come back. We're still pretty short. Okay, and as the clock ticks over, the numbers start to tick up.
And I was one of the lecturers on the first Heliophysics Summer School, so everything comes around. So when will you guys be the dean of the summer school?
I don't think we have any this year. I wonder if Allison was a former participant. I don't recall us having any participants this year. the lecturing. So, but we've had former participants who have come back and then lectured at the summer school. So it's
That's right.
the generations are starting to tick by. Okay, great. Still waiting for people to return. I am, however, going to share my screen. Yeah, I'll do the whole thing. I always feel at risk when I share the whole screen because I don't know what else is on there. But I rebooted my computer last night. So as a start, can you see my presentation?
Yes.
Okay, great. Thank you. As a start, before we while we're still waiting for a few people to return, do me a favor and rename yourself to include which expert group you were a part of, whether you were part of the solar wind, the magnetosphere, or the ionosphere. And you can use I started with a solar wind example, but you can use my shorthand here for the others, so that we can then have a good sense. And we're gonna have to this is gonna might require a little bit of reorganization, but we'll figure it out. Okay, so people are still trickling in. As you and I'm talking to the wrong people because these are all the people who are here. Maybe if you can log on a couple of minutes before the time that or even 10 minutes before the time, that would be great, and then we can start right away, and we're not waiting for people's audios to boot up and them to drop into the room. So, but I'll state that reminder again in a few minutes. All right. And I'm asking people to start to rename themselves with the expert group that they were in, the sort of shorthand for the expert group that they were in. Okay. We're going to start. This is a little bit of throwing you all in on the deep end. And maybe I can just check in with Christina or Mark and make sure that somebody's following chat so that I don't have to.
Yep, I got it.
Great, thank you. Yep. Okay. This is a little bit of throwing you all in on the deep end, but one of the things I'm relying on is the fact that for this particular summer school, one of our selection criteria is people with some research experience already in the heliophysics or space weather domain. And so you all have some expertise in this area already. In fact, many of you are probably the experts on what you're doing in this call, right? So that you know what you've been doing for the last few years. We don't. You probably, even though there may be, somebody like Lika, who has been around for a very long time and is aware of the whole gamut of things going on, she may not know specifically. She doesn't know the result you got last week. Right. So you're certainly the experts on in that. So one of the things that I rely on then is that you're going to be able to teach things to other people, right? And we're going to be able to draw upon that expertise. And that's part of what this exercise is about. It's also then about you meshing and with other expertise and figuring out how that all fits. Now, where this kind of breaks down is the time zone groups. I couldn't necessarily, because we've got those are specific to time zones, not necessarily every time zone group or every member of a time zone group was working within their own expertise to be involved. But we're gonna work with that for now, and we're gonna fix that. So let me see if I can move that. Yeah, great. All right. First off, so you're gonna work in your synchronous groups. So you've done some work in your time zone groups on this data. You're gonna work with your synchronous groups, and I'll explain what you'll be doing next with that. But one of the things that I'd like to remind you about is that your discussion should be, kind and inclusive. You're not only responsible for your own learning, you need to take responsibility for other people's learning as well. All right. And in particular, this is a good example of that, because again, you've spent some time looking at a particular set of data for this particular event that we're going to talk about. So now you've got to explain it to other people, and also then listen to them and see what they what their understanding is, and have a conversation back and forth. Another comment that I have on the questions that I ask in the lab manual. Those questions sometimes are some people take me a little too literally with sometimes with those questions. So I'll ask a question and the answer will be yes. And I'm like, yeah, this is a graduate and postdoc level summer school in space physics. I want something more, right? So the questions are meant to drive a conversation. So think about them a little bit deeper than the point of the question is not to get an answer. The point of the question is to drive the conversation. All right. And so I would like you to go beyond those questions, use them as a jumping off point, but then talk more with your group and try and expand on what you your discussion. Whoops, shoot. Okay. In your expert groups last night or over the weekend, what I hoped would happen is that you would look at the particular data set that you were given, whether it's the solar imagery or the in situ data for the solar wind and the models for the solar wind, or similarly for the magnetosphere and similarly for the ionosphere. Look at those particular data and identify where some key features were. Where was the event? Where was an event where that you might be important? Where did it happen? Some of you have already started. I'm looking at the boards and starting to make connections across those those silos that I put you in. And of course, it's exactly what you should be doing, right? So the silo I created was artificial, and you already have the instincts that you have to look at something. If you're looking at the magnetic field data from GOES or the magnetic or the simulation data of the geospace, you better be looking at solar wind. So some of you already have started doing that. And then try and understand at least the pieces, so the details of that data. So now what I'm going to have you do is I'm going to have you work in your jigsaw groups. And the jigsaw groups, so your synchronous groups are what I'm referring to as your jigsaw groups. What you're going to have to do now is take the individual data sets from the sun, from the solar wind, from the magnetosphere, and from the ionosphere, and start to weave them together into a story of this event and tell us what happened, right? And tell yourselves what happened. So you're going to build a prescription of the whole event. I would say you might start by reviewing the results from the expert group data. And so each of the experts start to go through that. But at the same time, you're going to want to start harvesting some of that data, because you're going to use it on your own Miro board. And I'm got to post that in a minute. I've got the links to 14 Miro boards for each of the 14 groups that we have. And you're going to want to make a mind map. And I'll explain what I mean by that in a minute. you may not want to do these formal roles. Sometimes they're useful, sometimes they're not, but you should be at least be thinking about this. There are a few roles. There should be, ideally, if we've got everybody here, and I can see by the number that we don't, ideally there should be 5 people in each group. But one person should act as the facilitator, making sure that everyone's included in the discussion, making sure that everybody agrees with the conclusions that are being drawn or doesn't have any questions or concerns. Another person may be acting as the recorder, okay? Somebody starts, in this case, somebody starts to grab materials as they are being discussed in the expert group and dropping them into the mural board that you're going to create. And then finally, somebody ought to be paying attention to the time and the tasks, right, that are required. So if you're 45 minutes into this and you haven't, and your mural board's still empty, you know, somebody should say, hey, we gotta do something about that. We gotta move on. All right. Here I'm gonna switch over to, yeah. I'm gonna try and switch over. Where'd it go? Uh-oh.
Was that Michael Faraday?
That is my hero, Michael Faraday. Yes.
Awesome. Mine too.
All right. I've created 14 copies of this, and it's pretty empty, right? So if you zoom out, right, I've just got some little template going on here. The idea here is that you're going to use these components to map out what happened in this event. And so, and I'm thinking about 3 different pieces of sort of ideas here. One is just data, okay? And that data could be a specific value. For example, a GOES X-ray flux, okay? It could be a graph. It could be an image of the sun when the flare goes off. It could be a model result of the impact of a CME on the magnetosphere, right? So I'm including the model results in with the data. So in that, you may then have the concepts. Okay, so for example, you might have an image, a coronagraph image, and that shows a bunch of stuff, but then the concept is, oh, I can see a CME here. Similarly, you may see the CME in the solar wind data. So you're going to want to have that. And so the data can then be identified with a particular concept. So it can also be identified with the data source itself, but then it can be identified with a particular concept, and that concept could be, you can put, you know, anything you like in here, solar flares, CMEs, etc. That concept is going to either impact or drive something. A solar flare is going to impact the ionosphere. Okay, a CME is going to maybe impact the standoff distance of the magnetosphere, etc. So then you're going to want to drive that, and when that, so you're going to see what it drives, and then that should then show up in a new set of data, right? You may find that this lays out in a nice timeline. You may find it's a little more, I hope it's a little messier than that, right? That there's other things going on, that there's pieces that feed back in on themselves. So that's something that you're going to want to do. What I hope is that everybody's looks different. Questions on I'm not done yet, but questions on anything that I've said so far regarding what we're doing or what you're going to be doing.
I have a small question.
Yeah.
So as for example, for the data, if we want to use as for example coronagraph or as for example tech map, we just like list like all together this kind of data, or we do like a sort of timeline for each area. So like
So
one,
I think it's individual pieces of data. So if you've got a coronagraph at a particular time,
okay,
you take the screenshot of that and drop it in here.
okay,
And you're going to want to link that.
Okay, but we like put all the data in this kind of timeline, or we do like this kind of schematic, like one for the ionosphere, one for the I don't know.
So
I don't know if you got me. You got what I want.
I want, at this point in time, I want you to get out of your silos and start linking things together. So if you've got data from the ionosphere, why is that, you know, particular, there's an event there, why is that there? What's driving that? So where's that coming from? So you want to work your way back to something.
Okay, okay.
Does that help?
Yeah.
Okay. Yes, the results that, oh, thank you, Christina. Yes, the results should do the whole thing. It should show the whole event. Okay. Any other questions on that? Nope, that's from tomorrow. Great. There's one more thing that has me in the back of my mind that makes me anxious. I don't know that each synchronous group right now has an expert from each subdomain. Okay, that is a solar wind, a magnetosphere, and ionosphere. So I'm betting on and it may be a null set, but I'm betting on the large numbers helping me out here, and that with 5 people, there may be a possibility that there's an example in all of them. We're going to send you off to your groups in a minute. When you get there, do a quick inventory. That's why I had you rename yourselves with solar wind, etc. Do a quick inventory, see which experts you've got available. If 3 of the 4 experts are available, continue on, and when you get stuck on something, call for help, and one of us will drop in and help you. If less than 3, 2 or 1, that is, are in your group, yell immediately, and we will fix things on the fly. May combine you with other groups or something like that. Okay, so we will see what comes of this and how this works. So I think, unless there are any questions in chat, can we get access to the new mural? Oh yes, I'm gonna put that in as soon as we go to the breakout rooms. I'm gonna put that in Slack. It'll just be a list of the group number and and there'll be a link to the board. Great. Good. Okay, Shelley, let's
Yeah, and I do have one request. Go to the room that you're assigned to start with and stay there for a minute so that I can go through and find out who we're missing. And then if you've got one person in your group, or as Mark was saying, you don't have everybody in one area, then we'll reassign you, but just hang out there for a minute until we can find out who we're missing, please.
Yep, and we're gonna work on this till for about an hour or so, and then we'll come back together and start to wrap it up.
Nick, you're still sharing your screen.
Oh, I'm still sharing my screen. Thank you.
Mhm.
And I think, Shelley, we can kill the recording now, or at least pause it. Disturbance going on with the in the ionosphere, and from that back out, estimate what the TEC is going on. So there's a little bit of a chain involved in that data. Also notice that there can be both positive and negative effects. Not everything enhances the ionosphere, and in some cases, things can sometimes detract from the ionosphere. So you may notice, for example, here I have two TEC maps lined up one's from the February 1st. So a couple of days before the first storm hits, and then one's in February 3rd. So you'll notice in North America, you get an enhancement in the just before the sunrise. I'm assuming that sunrise is somewhere here, right? So you get some enhancement just before sunrise compared to the previous day, especially in the northern latitudes. But then right over the Atlantic anomaly, looks like there's a little bit of a decrease in TEC. And so this is the interesting thing about this is both positive and negative effects. All right. So from that, we can start gathering some of the data. For example, we can look at the solar wind data from both ACE and Discover. One of the things to note is that the two satellites, even though they're both at L1, they don't always agree. And that could be because they aren't exactly in the right space. It also could be because they aren't exactly the same instrument. So that's one of the things to keep in mind when we're looking at data is, not all data is created equal. So I both understand my understanding, and certainly Mark and Christina, I invite you to jump in if there's anything particular that you see. My understanding is there's some issue with the calibration of the plasma instrument on Discover, but you can also see that there's dropout in the ACE at this point in time. It's getting a little long in the tooth.
Yeah, ACE has gotten old enough that it can't do very well when the solar wind goes really slowly. So when the density goes really low or the speed goes really low, they can't get a good measure of the parameters. And so they basically just leave that data out.
Right. Which we'll note on Wednesday when we look at some other, not ACE, but some other data that sometimes gets dropped and what happens when that data gets left out. Solar observations. I gave you some GOES X-ray flux data. I think I gave you a link to check the GOES scale. Note that this is barely an M-class flare, right? So we've got a flare on the 30th, and then there's nothing else interesting happening even on the 1st. Maybe something happening over here, which is kind of interesting and noteworthy. And we'll see that, and we'll see in a minute. Because if we look at, and I want to move this along, so I'm just going to skip to here. If I look at the coronagraphs, so we can go through here and we can figure out which region popped off and where the flare was. But if you look at the coronagraph, two interesting things happen, and this might be hard. I don't know, depending on your screen quality, how big your screen is. This might be hard to see. In fact, here I'm going to do is blow this up. Oop, too much. Shoot. There we go. So on the 30th, where that barely M-class flare happens, looks like you get a halo CME. And the halo CME is the one that's coming towards us, right? Because it's all you see is the halo around the sun as it's coming out towards us. And so maybe it's a partial halo. Oops, stop that. Maybe it's a partial halo here. It's a little hard to see, but then fast forward to the first, and then there's a couple of light bulb CMEs here and here popping off, but they may be going in the wrong direction. You get a little bit of a clue from those. So here's the halo, and that's a little better. This is from the stereo spacecraft, which currently at this point is off to the it's ahead of us. It's seeing the sun ahead of us. It's behind us in our orbit. It's ahead of us in the rotation of the sun, right? So it's looking at this from the left-hand side a little bit, and then you can also see that the two light bulb CMEs coming off this way. And so you may be able to triangulate a little bit from that. And so somehow we got a glancing blow from this CME. I'm not sure. That's where you'd have to go looking at the solar wind at the simulation results. And so what happens, the state of the art for simulating CMEs right now is it's breathtakingly awful, but it's the best we've got. Right. You'd think that there would be some like sophisticated, complicated thing of how do we do this. So this was a major innovation just a few years ago. You take a static solar wind, or maybe that's static, but a sort of quiescent solar wind based on the state of the sun. You take a model of that, and then you blop a bunch of plasma at the spot where you think the CME erupted, and let that evolve in. And the plasma has some average characteristics and some average. It doesn't even have a magnetic field in it. And so it's not particularly sophisticated. It's pretty brute force. Of course, back in the day, it used to be that you got out the pencil and paper and started making measurements of your CME to try and figure out when it was going to arrive. But this is how we do it now. So it's been an advancement, but not much of one. And you can see in the models, there's a wide range of arrival times for the CMEs. And then you get a second bump here, which may either be a CME or it's part of a co-rotating interaction region. It's unclear. So, and then we can look at the magnetosphere data. More importantly, you start to line up the magnetosphere data with the solar wind data. And in particular, you get a KP index, again, another index that's a measure of the disturbance of the magnetic field. And I hope that what you got out of this was that these geomagnetic storms aren't very strong. I mean, it's KP6, which is not, it's a storm, right? It'll cause some aurora someplace up north in Canada, but nothing really out of the ordinary. Here's the cautionary tale. And this is now, when I first was doing this, this paper was in preparation. It's now been published in Space Weather Journal. And the cautionary tale is comparing your models, right? So here we've got two models of the ionosphere, the NRL MSIS model, and I don't ask me what that all stands for. And then the WAM model, again, don't ask me what that all stands for. But in this case, the WAM model, the important thing is that the WAM model has a much higher resolution in its grid spacing than this particular NRL, this particular MSIS model. And so because of that, what happens is the spacecraft at they don't give the altitude, 210 kilometers, where the Starlink spacecraft were starting their orbit insertion, you can see that there's a lot more variation in the density of the ionosphere and the thermosphere at that, or in particular the thermosphere, the neutrals, at that height than is shown by this model. And that variation in density is going to give you a variation in the orbits and also the forces on the spacecraft. And so it's going to change how the spacecraft is going to respond in terms of its drag. So the density is high enough that once the solar panels on these things deploy, the satellite drag picks up and it starts to do a lot of bad things to the spacecraft. I'm not going to go through this, these charts. Again, this is from the paper. You can read that. The important thing is that at the time that this is all going on, when the Starlink satellites get inserted, some of them start to tumble. And so they deploy their solar arrays, they get hit by varying drag forces, and they lose control of the spacecraft. So even these graphs showing the attempts to do orbit insertion are only a fraction of the spacecraft that were supposed to be on the launch. There's about 50 spacecraft, and they immediately lose a whole batch of them, and they can't get them because they can't get control of them. And then they lose some more because they can't get them into orbit. So message is the space environment is, so they like to say around here in New England, we're having some weather, right? So yesterday we had some weather, right? Meaning that there was a storm of some sort. And I like to say we're always having weather. Right? There's always weather, whether it's sunny outside or a storm. But there's always, we're always having some space weather. There, you've got to account for the space environment at all times. And even minor storms can have an impact, especially if you're working on the margins. So if you're trying to do something clever. Okay, great. Questions on any of that? I saw that the chat was very active, but Mark was taking care of it. So
Mark was contributing completely. Yeah, and a question.
But there's two questions. Yeah.
Oh yeah. Sorry.
One was on what can be done, and my understanding of the Starlink philosophy is, as they're trying to launch 30,000 spacecraft, essentially a assembly line. They recognize that out of a batch of 50 to 60 or whatever satellites per launch, there could be some failures. And so they actually launch the satellite into a relatively low Earth orbit. So if there are failures, that they will decay quickly, and so will not cause any orbital debris issues. But they, for whatever reason, didn't anticipate that at that low altitude during a geomagnetic storm, the density could rise quickly enough to cause loss. And so they're trying to balance at what altitude they can get away with launching junk that won't stick around for a while, and then once they've successfully turned on, boost them up. So.
And what was where was the other question? I don't see it. Was there another question?
Oh, well, Andreas just had a comment, I thought, which was interesting.
Yeah, I can maybe
Andreas,
speak back then, like just when this happening, obviously people were very happy because it finally showed like some space weather effect. But if I remember correctly, like, this is secondhand information that there was some people at conferences who stood up and made claims that they were able to show that this was not space weather related. The problem was I never actually heard any follow-up information on that or who actually made these claims. So I'm wondering, was there any publications regarding this event that where people claimed that it had nothing to do with it?
The only publication of this event that I'm aware of is Zhui's Fang's publication. It's not just her. It's actually a combination of people from both SWPC and SpaceX on this, and they do a pretty detailed analysis of to make the case for better ionosphere models, and that it had better models been available, had better models been used. They were available, they just weren't being used by SpaceX, that they would have known, they would have had some indication that something was going to happen. So
okay, so they were able to make the case very strongly that this was actually what happened.
Certainly, it went through a peer review process, and you know, so yeah. So when you have that link in the lab manual, or the reference in the lab manual. All right, great. Anything else from today? All right, I have two things for you all, I think. First, in an effort to continue to make sure that we're doing a good job now, and also improve for the future. I have a survey, a day, so it's going to be the same survey every day. And it should take you about 5 minutes to fill out. I would ask you to start to do it right now. And so I'm putting the link in the general channel right now. And then the other thing in the time zone work, let me just check and see that I did this. Yep, great, that's the right one. I'm putting a PDF. So in your time zone groups, I'm going to ask you to look at, oops, where'd it go? Nope. That's not supposed to be. Yeah, okay. You should have a PDF in there now, and I'll write something. So as part of your time zone groups, so you should get together with your time zone groups today. Well, over the next 24 hours or so, or 18 hours, however long. Go through activity 1. Okay, you only need to do activity 1. And part of the goal is just to learn how to use the Helio viewer. And so that when you're coming in tomorrow, you can get right to work on some of the other stuff. And also a review of the types of data that are available from SDO and SOHO observations of the sun. So, and I'll write a little bit more instruction on that. But that's your job. So complete a survey and work on this in your time zone groups. If your time zone group is having trouble getting together, please let me know. Let one of us know. You can message me on Slack, and we'll see what we can facilitate, or if there's a different arrangement that needs to be made. All right. Questions, comments? Deadline for activity 1 is like before our session tomorrow. All right. Great. Thank you all for your work. I appreciate it. I was listening on many of the no, this is activity, sorry, Bijoy. This is activity 1 from the manual I just posted in Slack. Okay. Thank you all for your work today, and we'll see you all tomorrow.
Hi, Nick. Just a quick question. Is there a Miro board to summarize, like to write all the answers, or it should be just? There
is a Miro board, not for the answers per se. I don't want all of the answers. What I want at the end, so there's some instruction right at the end of the activity 1 with a link to a Miro board where you post a screenshot of what you're going to create, and write some text, a little bit of text to respond to some of the questions. Please don't write a thesis.
Okay.
I want a few indications of, like, indicate some features in this image that you posted, and write a few comments.
Thanks. Yeah.
And everybody's sharing the same Miro board. Well, all the groups are sharing the same Miro board. So I just need one image per group. Okay? Great. If there are any other questions, we're available. And if there are any questions about today or any logistical issues, we'll be available. If not, we'll see you all tomorrow.
Thank you. Bye.
Bye.
And Wisha.
We have a quick question from the slides you showed about the TEC plots. You showed that in the northern hemisphere there was an enhancement just before the dawn, and in the southern hemisphere there was reduction. What exactly is the physics playing out there, and how is that hemispherical thingy matched?
Yes. I am not going to be able to answer that question. That is beyond my ability to respond. We need an ionosphere physicist to be able to tell you about the variation in the winter anomaly when the Appleton fountain is running in the, like, blah 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 blah. I can't follow all of that. So yeah, unfortunately I don't have that. I mean, the complication in the ionosphere is that it's it's not only like a sort of standard, a nice standard plasma physics, but there's also then the neutral winds that are running at the same time that are being coupled from below and above, and being driven by sunrise and sunset and the diurnal heating and that sort of thing. So, and diurnal heating and then seasonal heating, and so so I am not going to even try to explain why you're getting one or the other.
Okay.
I
thought maybe I missed something simple, but
no,
okay.
No. I think the only point that, I mean, the point I like to make is that it's not a simple system, and that you can get both enhancement and suppression. So what the ionosphere physicists refer to as positive effects and negative effects.
Okay.
And so and why those things happen again, has to do with a lot of different properties. Oftentimes you have to go to a model, look at the event, say, aha, there was a change in the recombination rate because of, some depletion of a particular ion or something like that. I mean, I'm making stuff up right at this point in time based on what I've overheard. So I'm sorry I can't be more helpful.
Okay, thank you. It was a great day. Looking forward to tomorrow.
Okay, good.
Nick, Rahab had a question in chat about what they're supposed to do. She lost part of her connection.
Oh, okay. So first, complete the survey. Second, get together with your time zone groups and review activity 1 on the manual I just posted. Is that good, Rahab?
Yeah, it's fine. I lost my connection. The last thing that I know that we have to do activity 1. So I was asking if there's any other thing that I must.
Nope, that's it.
Okay, thank you.
You look like you're in a place where the wind is blowing.
Yeah, a little bit. Just it's too hot here, so it's lighting.
Okay. All right. Anybody else have questions or issues? Maybe people can drop them in chat or something else. All right, I don't see any other questions, so we'll see you all tomorrow. And I'm gonna hang out with Shelley and discuss any logistics issues. So.
Nick, I sent you a email about the activity for Wednesday. I don't know whether you got that. Okay.
Yep.
So we can
touch
base on that later if you want.
It is on my mind to try and yeah, I think it might be easy. I'm trying to think I think it might be easier for me to like take the data files and